Hi, welcome to your Mac 200 Statics online classes. In this video, we are going to continue the content of Chapter 2. This is the second of a series of 3 videos in which we review the mathematics behind operations with vectors. I hope you enjoyed this lecture. Let's continue from where we left in the previous video, talking about the addition of force vectors. But now we're going to focus on situations when a force needs to be resolved into two components along orthogonal axes x and y. In this case, the components are called rectangular components, like in this representation here. We're going to start with the scalar notation, in which the rectangular components of a force F are found using the parallelogram law, so that F is the vector sum between its projection in the x-axis, Fx, and its projection in the y-axis, Fy. Because these components form a triangle, their magnitudes can be determined from the following trigonometric relationships, using the cosine and sine of the angle theta, respectively. An alternative, but useful way to represent the direction of F, other than using theta, is by defining a small slope triangle similar to the big shaded one in this figure. Then, using this notation, the components Fx and Fy are given by the following equation. If one of the components is oriented in the negative direction, like the y component in this figure right here, then their magnitudes are calculated using those equations, in which the y component receives a negative sign. It's also possible to represent the x and y components of a force through what we call the Cartesian vector notation, which uses the Cartesian unit vectors I and j. These two vectors are called unit vectors because they have a magnitude of 1, with no dimension, and they are used to designate the directions of the vector in the x and y axis. Since the magnitude of the components of F, which are Fx and Fy, are always positive scalars, then we can express F as a Cartesian vector according to this equation. In this notation, components pointing towards the negative x and the negative y directions will always have a change only in the direction of the unit vector, being expressed by -I and -j. Also, it's important to mention that for handwritten work, unit vectors are usually indicated using a hat sign on the top of the letter. Now let's apply the scalar and the Cartesian vector notations to determine the resultant of the sum of several coplanar forces. Coplanar forces are the ones that act along the same plane, like in the figure shown here, in which all the three forces act in the xy plane. To add them, we have to decompose the three vectors in the x and y directions. For the force F1, we have both the x and y components oriented along their positive directions, and then we write its Cartesian notation like this. For the vector F2, we do the same, observing that the x component is oriented in the negative direction, and then we have to represent it using the negative I unit vector. And finally, the vector F3 has its y component oriented in the negative direction, and we represent its Cartesian notation using the negative j unit vector. Next, we calculate the resultant force by adding the x and y components of the three vectors using scalar algebra. For this, we just have to replace the x and y Cartesian components of F1, F2, and F3 into the resultant force equation, making sure that in order to perform the scalar algebra, the negative sign should pass to the magnitude of the components. Then the next step is to group the magnitudes of the components according to their orientation in the x and y directions. And finally, we isolate the components of the resultant vector. We can easily extend this approach for any number of coplanar forces. A convenient way to do it is through the algebraic sum of the x and y components of all forces represented by this general equation. Once we have determined the components of the resultant force, they can be sketched along the x and y axis with their proper sense of direction, and the magnitude of the resultant force can be found from the Pythagorean theorem. Also, we can specify the direction of the resultant force through the angle theta using simple trigonometry, which is given by the arctangent of the magnitude of the y component of the resultant force divided by the magnitude of the x component of the resultant force. Before we go to the practical examples, let's highlight the following important points about the addition of Cartesian vectors. The first important point is that, after we establish an xy coordinate system, the resultant of several coplanar forces can easily be determined by resolving the components of the forces along this axis. The second important point is that the direction of each force is specified by the angle that its line of action makes with one of the axes, or by a slope triangle. Those are essentially the two ways we've learned here, and both can be used dependent on the problem that we are trying to solve. The third important point is that, for all vector problems we solve, the orientation of the x and y axis is arbitrary, and their positive directions can be specified by the Cartesian unit vectors I and j. The fourth important point is that, through the Cartesian vector notation, the x and y components of the resultant force are simply the algebraic addition of the components of all forces involved, if they are coplanar. Later in this video, we'll learn how to do a similar operation if the vectors are not located along the same plane. And the last important point is that, once the components of the resultant force are determined, it's easy to calculate its magnitude and direction from simple trigonometric relationships, such as the Pythagorean theorem and the arctangent of the direction angle. Now let's work on examples. In this example, we have to determine the x and y components of F1 and F2 acting in the boom shown here, and express each force using the Cartesian notation. In this problem, we are given the magnitudes of F1 and F2, the angle of F1 and the y-axis, and the dimensions of the slope triangle attached to F2. To solve this problem using the scalar notation, we start by applying the parallelogram law to F1 to get its x and y components. One can observe that the x component can be found from the sine of the angle 30 degrees and acts in the negative direction. And this should be reflected in the answer as a negative scalar value for this component. On the other hand, the y component acts in the positive direction, and its magnitude is calculated using the cosine of the same angle, which results in a positive scalar value. For the force F2, we do the same, but using the proportion relationships given by the slope triangle, which results for the x component of F2, 240 newtons. And for the y component, keep in mind that it is oriented in the negative y direction. The slope triangle gives a value of minus 100 newtons. Then, we have to solve the second part of the problem. Since we have already calculated the magnitudes of all components of F1 and F2, all we have to do is to take the x and y components of F1 and write them in the Cartesian vector notation. We do the same for F2, and then we get the final answers. You're ready now to study examples 2.6 and 2.7 of the textbook on your own. Once again, try to fully understand all steps involved in their solutions before you start solving the practice problems of this chapter. Now let's turn our attention to vector algebra operations when applied to solving problems in 3 dimensions. We can easily see that this task is hugely simplified if the vectors are first represented in the Cartesian notation. In order to do this, we use a right-handed coordinate system to develop a simple theory of vector algebra. But why using the right hand? Because we can easily come up with a rectangular coordinate system if we consider that the right thumb points in the direction of the positive z-axis, then the other fingers are curved around this axis, directed from the positive x-axis and towards the positive y-axis. Just to put in simple words, the z-axis is aligned with the thumb, whereas the x-axis is aligned with the proximal phalanx, and the y-axis is aligned with the fist. Now, let's use this coordinate system to represent the 3 rectangular coordinates of a force vector f. First, we need to project f in the xy plane to get a force f prime, and then we resolve the components of f prime in the x and y axis. By doing this, we can write f prime as a vector sum of the components fx and fy. Next, we resolve f into the component along the z-axis, fz, and we write f as a vector sum of the components f prime and fz. By making this substitution, we are actually writing f as a vector sum of the components fx, fy, and fz as we wanted. If we want to move further and write f using the Cartesian vector notation, we have to establish the unity vectors I, j, and k, this last one oriented towards the positive z-axis. Then the result will be this Cartesian vector equation, since the 3 components of f act in the direction of positive I, j, and k. Once we have done all of this, we can calculate the magnitude of f from trigonometry, which is equal to the positive square root of the sum of the squares of its components. Also, we can define the direction angles alpha between the force F and its component in the x-axis, beta between the force F and its component in the y-axis, and gamma between the force F and its component in the z-axis. And then alpha, beta, and gamma are calculated using the cosine relationship between the magnitude of F and its x, y, and z components, respectively. Because of the nature of these 3-direction angles, this important relation among their cosines can be formulated. The advantage of having this equation in hand is that if 2 of the angles are known, then we can get the third one. Finally, if the magnitude and direction angles of f are known, then we can express f through this Cartesian vector form. Sometimes the direction of f can be specified using 2 other angles, which are referred as the transverse angle theta and the azimuth angle phi. The transverse angle is defined by a triangle formed by the project vector f prime and the x-axis, and the azimuth angle is defined by a triangle formed by f and the z-axis. Then we can write f in the Cartesian vector form using this equation as a function of the transverse and azimuth angles. With all this background on Cartesian representation of force vectors, we are now ready to present a generic formulation for the addition or subtraction of multiple vectors. Let's consider that we have 2 force vectors, f and x, mathematically represented by this Cartesian vector form. Let's then say that we want to add them to find the resultant force R. A convenient way to do so is through the decomposition of R into its x, y, and z components, which will be the sum vector of the components of f and s individually. We can then write the resultant r in the Cartesian notation using the I, j, and k unit vectors, which for a system involving several concurrent forces, the resultant force is the vector sum of all forces in the system. In this equation, the summation symbols represent the algebraic sums of the respective x, y, and z components of each force in the system. Let's then recap the most important points we have talked about Cartesian representation of 3D force vectors. The first important point is that a Cartesian vector has the x, y, and z components represented by I, j, and k unit vectors along this axis. Then the second important point is that if the components of a vector f are known, its magnitude is defined as the square root of the sum of the squares of the magnitudes of its components. The third important point is that we can use the angles alpha, beta, and gamma measured from the positive x, y, and z axis to express the direction of a Cartesian 3D vector. If only of those two angles are known, the third one can be found from this cosine equation. And the last important point is that another way to represent the direction of a Cartesian 3D vector is using the transverse angle theta and the azimuth angle phi. Now it's time to work on examples. In the example 2.8, we have to express the force F shown in this figure as a Cartesian vector given its magnitude of 100 pounds and the two reference angles of 45 and 60 degrees. It's important to freeze here that these angles are not the coordinate direction angles. It's extremely important to recognize this information at first to not incurring any mistakes in the calculations. To solve this problem, we have to apply the parallelogram law at least twice in order to resolve f into the x, y, and z components. Let's start with the component in the z-axis that we obtain by taking the multiplication between the sine of the 60 degrees angle and the magnitude of f, which results into 86.6 pounds. If we take the sine of the same angle and multiply by the magnitude of f, then we get the magnitude of f prime, which is 50 pounds. Now, let's take the 45 degrees angle. If we multiply its cosine by the magnitude of f prime, then we get the component of f in the x-axis, which is calculated as 35.4 pounds. Likewise, if we take the sine of 45 degrees and multiply it by the magnitude of f prime, we will have the component of f in the y-axis, which is also 35.4 pounds. Then, with the magnitudes of fx, fy, and fz we've just calculated here, and having in mind that only fy acts in the negative direction, then we have this final answer for the Cartesian notation of the force vector F. With this example, you should be able to study the example 2.9 of the textbook on your own. Try to fully understand all the steps involving their solutions before you get started with some of the practice problems in this chapter. And that's the end of the second part of chapter 2. Thanks for watching, and I'll see you in the next video.